So welcome to our reaction mechanism video of our kinetics unit. Speaking about the speed of reactions, we want to break reactions down because it's really unlikely to have, let's say, a trimolecular reaction where something reacts with two particles of something else. We know that the reaction has to happen with the correct energy, so sufficient energy, and then the correct orientation. All of this is really difficult. So oftentimes what we see is an overall reaction. We see a net reaction. We don't actually see all the little sub-steps that are happening behind the scenes. So this lesson is about sort of unpacking all those little steps. So here we see a reaction that's occurring in two steps, but let's say in a textbook we might not see all of these. We would just see the overall or the net reaction. So what our job is to do is to sort of like almost like squeeze it down, kind of like, gather like terms, if you want to think about it as algebra, kind of cancel out some things. So certainly this arrow is, a little bit like an equal sign where, we'd speak to just reactants on this side and just products on this side. And so if we look at this, we can actually see that here we have the selenium oxide, and over here we have a selenium oxide, and it's something that gets created but then gets consumed. So in step one, selenium and oxygen react to form the selenium oxide, and it's here, but then it gets used up as it meets more oxygen. And so for all of the selenium oxide that gets created, it will also get consumed. So this guy actually cancels itself out. And so that we can call a reaction intermediate. So we see it as a product. Then it gets consumed as a reactant in a subsequent step. So reaction intermediate. And the things that we see now as products, we don't see again as reactants. So I think it's time that we can kind of compress this, sort of squeeze it all together, and say, all right, I'm going to have only one Se on this side. Now I'm going to have two oxygen molecules, and over here I'll have one of this SeO4. Overall, we also have some description about the steps, like about the rate of each of the steps. So what we would have is we'll also have a rate determining step, or an RDS. So rate determining step. That's going to be our slowest step. So let's say you're walking with a group and you're trying to all get to a certain place, but you can't enter until you guys are all together. Well, you might be able to walk there super fast, but you're still waiting on somebody else in the group that's at the back. So your whole group is being determined by that slowest walker. And so that's what happens here with our reaction, is that we want to look to the steps and say, which one is our slowest step? That is the one that's going to determine our rate. And so we see step two with this descriptor of very fast. So we know that step two happens like immediately, but the whole reaction itself will be considered to be slow, will be the rate, and the rate determining step is step one. If we wanted to, we could also sort of graph out a potential energy diagram for these two steps. And we would use this descriptor about the heat. So being endothermic, we'll be having a positive delta H, or positive change in heat for the system, as opposed to step 2, which is exothermic itself. So we're going to take these kind of one step at a time. So first I'm going to be drawing out step 1, which is our slow step. So by slow means that, you would have a high amount of activation energy that's required. So I might draw a really big hill for slow, because that shows that there's a large amount of activation energy required. Then for endothermic tells me where I can put the bottom of my hill, if you will. If it was exothermic, I would want to put the bottom of the hill here, so that the delta H relative to the reactants, so that these products would be lower than the reactants in terms of overall heat of the system. But for an endothermic reaction, I want heat to flow from the environment into the system, and to have a positive delta H here. The second step is very fast. So by very fast, we want to make sure that this is bigger than, let's say, this. So let's just make it a little one, right? Because it's very fast. It doesn't take much energy to get up and over it. Now, this is saying exothermic. So by exothermic, we can bring this down below where the reactants were. And overall, this reaction is supposed to be exothermic, which means relative to where it actually began in the first place. So we can actually bring this all the way down here. Had this said endothermic, then we would want to, let's say, stop here. So it's exothermic to the second step, but endothermic overall. But of course, in this reaction, we want to be able to see that this is overall a negative delta H, or exothermic overall. Let's take a look at another one. So here's another reaction mechanism. Our goals generally are always the same, and it's to find out what is that net reaction. So we want to look at the products, the reactants, see if there's any way of sort of canceling some things out. Were some things created and then destroyed? So I'm looking right here. I'm seeing these guys. This OI ion that has been created in step 1 and then consumed entirely. So I would want to make a little note to myself that OI is a reaction intermediate. We see it as a product first, and then it's consumed in a subsequent step as a reactant. Don't get this confused with activated complex. Sometimes folks do confuse the two, but so this another thing that we can look for here is things that are presented as reactants, and then we also see them as products. So they're there at the beginning, and then they're there also at the end. So on the product side. And so that I would invite you to look at this iodine ion. We see it present at the beginning. We see it present at the end. When we write our overall net reaction, we're not going to write them on both sides. But what we do want to do is take note that so they actually cancel, that the ion is a catalyst. And So from factors, we know that catalysts have the ability to lower the activation energy, and they're like enablers, right? So in this case, the hydrogen peroxide doesn't want to just start breaking down, but it does in the presence of iodine ion. So that is acting as its catalyst. And again, we're going to see that as a reactant first and then again as a product. So now that we've sort of eliminated any sort of duplicates there, we can add together the two steps. So 2 molecules of hydrogen peroxide decompose to form 2 molecules of water and oxygen gas. But, I think it is worthwhile to note that it is in the presence of iodine ion. So that is our catalyst. If we wanted to draw a potential energy diagram for these two steps, we could look at these guys and say, okay, the very first step is a fast step. And so for a fast step, we don't really give too much of a hill or activation energy. There's not much activation energy required here. We also notice that this is going to be endothermic. So we're not going to bring the hill all the way down here because that would make that an exothermic reaction. So we're just going to bring it, let's say, here. And I do kind of want to exaggerate the difference between fast and slow, right? Like I could tell that this is supposed to be the big one and this is supposed to be the small one. Then the endothermic also for the second step and overall endothermic. Perfect. That's easy. Let's just do that. So endothermic for the first step, endothermic for the second, and also endothermic for the overall. We have a fast step compared to a slow step. And by slow, it's because there's so much activation energy that is required. And we can, oops. If we wanted to ask ourselves, what's the rate determining step? What holds this whole system back? What determines the rate? We would say not the first step, but the second step. The second step is the slowest step. So step 2 is the rate determining step. And then if you wanted to say, what is the rate? The rate is slow. And that's because of this descriptor here. If it said very slow, then the answer would be very slow. But you can only go as fast as your slowest step.